All right, in this video, we're going to look at this kind of theoretical question here from 4.9 example 4, looking at critically damped motion. We're going to try to prove mathematically and then understand physically what's happening here, but try to prove why this can have just a single, if any, relative extreme. And so we're going to do that and just assume that it has some initial conditions here, an initial position and an initial velocity. We're going to try to show that it can have at most one relative extreme. So let's do that. Let's use those initial conditions like we normally would and try to solve and express the A and B in terms of those. So let's see, restating here, x of t is a plus bt e to the rt. So x of 0 would be a e to the 0, and that's it. So that would be the initial position. So a is the initial position, easy enough. X prime of t, we'll have to do the product rule here, so that would be b times e to the rt, plus a plus bt times r e to the rt. And if we factor that out, e to the rt, we'd have b plus, a little clunky here, r times a plus bt, or e to the rt times b plus ra plus rbt. All right, and we want x prime at 0. We'll represent that with the initial velocity v naught. So x prime at 0 will be, let's see, that'll just be 1. And so we'll have b plus ra, which will be equal to the initial velocity. And so b will be the initial velocity minus ra, but a is the initial position, so b is v naught minus r times the initial position. All right. So those are our initial, those are our coefficients. So let's look at the relative extreme. Now we know from Calc 1, relative extremes occur at critical points, which are going to be at places where the derivative is 0 or undefined. So let's look at our derivative. This derivative is a smooth function. It's never undefined, this function is never undefined. So this function has no cusps or vertical tangent lines, but it can be equal to 0. If we consider x prime of t equal to 0, this exponential factor here can never be 0, but the rest of this could. B plus RA plus RBT could equal 0. We could solve that. Let's see, RBT equals negative B minus RA. And then if we divide by RB, we get this kind of clunky expression. T is negative B minus RA over RB. So let's think about that just quickly here. We can plug in what those values are equal to from our initial position and initial velocity, but the one relevant point I want to mention here is, of course, if b itself is 0, then this is impossible. So one possibility is if b is 0, then there are no solutions to this, right? There are no critical points, there's no relative extremes. What that is if you think of physically what's happening there, and it depends on the relationship between the initial position, but I think, I don't know if we have time to delve into it, but that would be like, so we compress our spring a little bit, we start up here, and so our x has been shortened, but we release it downward maybe just slightly. Well, then it'll just kind of gradually flatten out. Now, if we push it down fast enough, it will pass through and then come back, but that's not this case. So this case would be, whatever your initial position is, you push it back toward equilibrium, but slowly. I don't know if that makes sense. So that's this particular case here. All right? Yeah, so this is where your initial velocity and the spring kind of balance each other out. That's this case if b is exactly equal to 0. The other case, of course, is if this numerator here is not equal to 0, so the b isn't 0, then there's some other possible solution here. So I'm actually going to go back to this. Let's consider this y equal to RBT plus b plus RA. And think of that like a linear function. So the solutions to this when it is 0 is when y here is equal to 0. But remember the b and the r and all that stuff, those had values. What was b? This is r times v naught minus r x naught t. B is v naught minus r times x naught. And then we have r times a, r times x naught. So what's interesting here is we just get r times, these are all just constants, right? These are all just constants from the initial conditions. The mass and the damping constant give you the r, and the v naught and x naught are the initial position, initial velocity. And then we have, actually all you have is v naught here. So what's crazy here is this is a linear function. This is linear. And so if we want to set it equal to 0, now there might be a negative time, which would be impossible. So that would be a condition where, you know, we push it down, but it's not perfectly balanced, but maybe the velocity is even smaller. And so the b ends up being negative, and, you know, whatever that is where you're pushing it here very slightly. But you could push it, maybe you compress the spring and you push it down very quick, you know, with a high velocity. It passes through the equilibrium and then flattens out. But there can only be, this can only be 0 once. It's linear. It can only cross through y equals 0 once. And so those possibilities are related to this. If you have your spring and you've stretched it and you push it and you stretch it even more, then it would stretch even more, but then return gradually to equilibrium. So that's one possibility. Another possibility is if you stretch it, that's a terrible spring. If you stretch it but push it up with a large velocity, then it could pass equilibrium. I'm going to illustrate equilibrium here like this. So it could pass equilibrium and actually compress the spring, and then over time return to equilibrium. So it could pass equilibrium and then return to equilibrium over time. So those would be represented here by, you know, and it's different combinations of the initial position and initial velocity, but the point is that this can equal 0 only once. And if it's a negative time, then it has no physical meaning. That means it's actually one of these that just gradually returns to the equilibrium position. So that's kind of a discussion there. A little precision, right? We delve into it a little bit deeper. We didn't really write down this explanation. We just kind of verbally spoke through that. But that's kind of the meaning of why that can have at most, it may have none, but it can have at most one relative extreme.